Okay, let's start to discuss what makes up an atom a little bit more. When we look at an atom, we have the nucleus. This is the core where two of our subatomic particles, the proton and the neutron, are held. And in the outside, we have where the electrons, our third subatomic particle, will be found. So again, it's really only three subatomic particles, meaning the pieces that make up an atom, that make up the atom for all different types of atoms. The protons and neutrons, they live in the center, and the electrons, they live on the outside. Now, how many protons and neutrons and how many electrons, this is what's going to define every atom's unique characteristics, which we will delve into very shortly, right? So the atomic number is the number of protons in its nucleus, and protons carry a positive charge. We call this the atomic number, and this is the most important number when we talk about an element. It is its identity. Its atomic number is the big whole number that you see located on that particular element. And as an aside, I highly recommend you print out a periodic table to have at your workstation for like all the work in this course. When we look at the atomic number, that identifies the species. So if we look at carbon, it has atomic number 6. If any atom has 6 protons, its name is carbon. If we ever have a carbon, it always has 6 protons, no exceptions. The atomic number defines the number of protons and the name, and this is what organizes the periodic table from left to right. As we move forward, we're going to see that sometimes atoms may have an electrical charge. So the protons are positively charged, the electrons are negatively charged. And if those two numbers are equal, then our particular atom will have a charge of 0. We'll look at this a lot more in future videos. When we look at the mass number, this is the total number of protons and neutrons in the nucleus. And for the mass number, we want to ignore the periodic table for a moment. It's true that the periodic table does tell us a little bit about the overall mass of an atom, but one element versus another element could have a different number for their mass, even if they have the same number of protons. Let's for now just consider that the mass number of a specific isotope, which we'll look at in a sec, is the number of protons plus the number of neutrons. So again, these are the mass-containing particles in an atom. The number of protons plus the number of neutrons is the total mass number. And so when we have atoms that are the same element, and again, the element is defined by the number of protons. If they have the same number of protons but different numbers of neutrons, we call them isotopes. Their atomic number will be the same, but their mass number is different. And let's take a look at an example here with carbon isotopes. On our left, we have this one in green. This is called carbon-12. And again, by saying that it's carbon, we actually know the atomic number already. It's 6 protons. Every single carbon always has 6 protons, no exception. This 12 here denotes its mass. So when we say carbon-12, we're saying carbon with a mass number of 12. And when we say carbon-12, we therefore also know how many neutrons there are. Mass number is 12, carbon means there's 6 protons, so the 12 total minus 6 protons means 6 are neutrons. Carbon-14, same thing, same carbon, same 6 protons, but now that we've said 14, its mass number is 14, and therefore there are 8 neutrons to go with. And if we think about carbon-12 versus carbon-14, the difference here is the nucleus, right? In carbon-12, the nucleus is made up of 6 protons along with 6 neutrons. Carbon-14 is 6 protons with 8 neutrons. This is different forms of matter, and we want to be able to communicate and discuss those different forms of matter. They may have very different properties. Okay, let's think about isotopes of iodine. And here we have a little chart with 3 different isotopes of iodine: iodine 127, iodine 123, iodine 131. Go ahead and pause the video here and try to fill out the top 2 rows, at least the number of protons and the number of neutrons. And I recommend you go ahead and Google a little bit about stability and uses. I'll share information about that coming up, but especially with regard to healthcare, these have relevancy. Okay, hopefully you've been able to fill out this chart as well as you can. Let's go ahead and take a look. Iodine 127 53 protons. And how do I know this? Well, it's iodine. And when we find iodine on the periodic table, it's got 53 protons because its atomic number is 53. Same goes for these other iodines. It's all iodine, all 53 protons. But what about the neutrons? How are the neutrons a little different? Well, iodine 127 has 127 total mass-containing particles. That's protons plus neutrons. And therefore it has 74 neutrons. 127 minus 53 that are protons, 74 neutrons. Slightly fewer for iodine 123, 70. It's got slightly fewer protons and neutrons. And iodine 131 will have 78 neutrons. So again, they all have the same number of protons. They're all iodine, but they have different numbers of neutrons. And when it comes to stability, which I hope you looked up a little bit of this, but if not, I'm happy to discuss this now. The naturally occurring form of iodine is iodine 127. This is the stable form. It's not decaying. It's the iodine that we look at like Morton's iodized salt, and there we are. Iodine 123, this is unstable, and if we have a pile of iodine 123, 50% of that will be decayed because it's breaking down, it's not stable, in 13.2 hours. We call that its half-life. Iodine 131, it's also unstable, and 50% will decay in 8.02 days. So it's not decaying as fast as iodine 123, but still will break down pretty quickly. And this is really useful in healthcare, right? Our stable iodine 127, this is our essential required nutrient, 100% of the naturally occurring iodine. It's important for your thyroid. It's important for a lot of metabolic processes. Iodine 123, this is used in nuclear imaging and scans because it emits radiation as it's breaking down. So we can provide a patient with iodine 123, and then we can monitor that radiation as the iodine travels throughout the body. And by monitoring that radiation, we could see where maybe a process is not going the way we would expect. For example, if there's some part of the body that's supposed to draw in iodine, and we see that it's not drawing in this iodine 123, we could see that that's the diagnosis, right? That particular function is not occurring normally. Iodine 131, similar, right? Nuclear medicine, it's also a big case. But absorbed by the thyroid, so a bit more focused on that particular organ. Both of these, though, really used for medical imaging. That's really one of the biggest use cases for these radioactive isotopes. They behave a lot like the naturally occurring form, but they're radioactive, so we can monitor them throughout the body. And if you have any safety concerns, yes, radiation could be ionizing. There's ionizing and non-ionizing radiation. But things to remember are this is not something that someone would do every day, that the isotope itself is decaying pretty quickly within the course of a week or a month. None will remain and could potentially be used to save a patient's life.